We're going to get started here. Thanks for joining our session. And my name is Hope Wang. I'm a developer advocate at Luxil and co-speaking with Bin Fan, who is the VP of Technology at Luxil. And today we'll discuss a very important trend of moving data-intensive analytics workloads to the cloud. And we'll take running Presto in production in the cloud at scale as a case study. And we'll present the challenges, opportunities, and solutions around that. Okay, let's get started. And then before we dive into the case study, and let's take a look at why we start this investigation or discussion and why this also matters to you. And now let's take a brief look at the evolution of the modern data stack. I know there has been some discussions in this conference, like yesterday there was discussion in modern data stack. I just want to highlight 3 of the most important trends here that is impacting the decisions of like moving data-intensive analytics workload to the cloud. And firstly is like 15 years ago, we know it was a Hadoop era, and we have a tightly coupled MapReduce, and HDFS is not decoupled. It's tightly coupled for performance and for ease of management. However, nowadays, we are decoupling these for better scalability so that we can scale them independently. And then the second trend I want to talk about is moving the workloads to the cloud. And we used to have like only one storage, like HDFS storage, the file system on-prem, and then we are moving them into the cloud data lake and using cloud object stores such as AWS S3 and then Azure Blob and GCS, so on and so forth, for cost and flexibility, and it has an infinite scale. And then lastly, we have the data access pattern also changed. We used to use the sequential access of record files, however, nowadays we're using the columnar file formats as Parquet or ORC dominate the data lake architecture. And these have been in the motivation of making your infra to run your analytics or AI workloads more elastic, cheaper, and then easier to manage and more efficient. However, it does come with costs. I want to talk about like 3 challenges here. And firstly, because you have separated your compute from your storage, so it loses the data locality. If you're familiar with the data locality, which is a principle for job scheduling in the Hadoop era, and now you have a separation of them, which means the data has to travel from the network to the compute engine. So it introduces some kind of latency. And then also from the cost perspective, like the cost model of on-prem and in the cloud is very different. I'll elaborate that later in my slides. And finally, we have sequential access pattern of row-based files to columnar files in the lakes, which means we're changing the data access pattern. It will also incur some kind of other optimization techniques and also affect the cost, the actual cost that we'll experience in the cloud. And let's take a look at like how the cloud cost model has evolved or changed all throughout these years. And in the on-prem days, if you're very familiar with that, in your data center, it has some upfront costs like infrastructure costs. You need the space, you need the racks, and you need all the hardware things to be ready until you can like run your workloads there. And then you have some kind of operational costs associated with that, like human costs and also like maintenance costs and for electricity and so on and so forth. And no additional costs when you're using them. However, things are quite different when you think about the cloud cost model. I've listed 2 tables here. The left-hand side is the cloud object storage cost from 2 largest cloud vendors. And the right-hand side is something called data transfer or egress cost, also from the 3 largest cloud vendors, which means every time you're retrieving data, like you having like put, copy, post list, or you have get, select, and depending on how they call the terms. And each operation or API call, you will incur some kind of cost, although it seems like a small number, but I'll have some calculations later on in my slides. And also from data transfer perspective, if you're only doing one region, like you're only doing the S3 US East, one, let's say, but that you will not have this data transfer cost. But if it's cross-region, it's charged based on the amount of data transferred. So the cost model is changed, which means every time you're using your data, although you put your data into these buckets, you dump everything there, it doesn't cost you much. But as you're using it, it costs you a lot. So the cloud cost model has changed, which means that we really need to rethink like how we want to optimize these data-intensive workloads in the cloud and how these are differently from the on-prem days. And then we have here, like, when we talk about a case study that we have some data to show, it's already in one of the papers we published. And this is the traces from a production Presto cluster from an industry leader in the Silicon Valley. And their cluster workloads patterns are like offline Presto processing traffic. As you can see from the left-hand side, and there is a cumulative distributed function over about 5 days. And these traces have shown us some interesting patterns you can see. First of all, and this is a really large Presto cluster, and it's handling 1 to 10 petabytes of data per day, which means this is really massive scale, which also means Presto is really like good at handling this robust and well-suited heavy-duty kind of data processing. And then on the other hand, and we see a lot of small data requests and dominates the I/O patterns. And you can see like half of the requests are under 10 kilobytes, and most of them are under 1 megabyte, which means, and you have a large amount of data processed every day, but each data request is very small, which means this is like a massive, like small request, but large scale, intensive kind of workload. And then we do a back-on-envelope calculation. If we have a medium-sized Presto cluster, let's break it down to this calculation. We have daily access data per day, like 1 petabyte of data per day, and then multiply with 10 billions of requests, which means we're calculating it based on 100 kilobytes per request on average. And then also like multiply by the calculation like pricing table I just showed, see it's less than 1 cent per 1,000 requests. And then calculate over 1 year. And you can see the annual cost is so big, like $1.4 billion per year, which means like the annual data access cost for that medium-sized Presto cluster can cost so much. And if you really overlook this kind of API cost, this is the main thing we want to discuss today. Although you see like it doesn't cost you that much for a single request, and when you have a scale, when you have like the small access patterns, you will like sacrifice from a very huge bill. And then, but here we have an opportunity based on, like we work with a lot of open source users, like we are from Alluxio and we are a cache layer, which means we have insights into the access patterns of different types of workloads. That we see an interesting number here we want to share is that less than 10% of your data is hot. I think it's something that people already know, that we have some hot tables that people actually frequently access daily, but we also have some tables that are not being used so frequently by users. And given this kind of data, and let's see how about we can use the concept of cache that is easy to understand, easy to theoretically adding that cache between the compute layers and the storage layers to reduce the number of the requests directly to the cloud storage. And now let's see like what are the benefits or the values that the cache can provide. Like it's really simple. It's like you cache the hot files or hot data in the cache layer, and instead of like directly retrieving from your object storage, so that you can not only like have some performance benefits, like cost benefits, I'll elaborate that later, and you can also reduce the number of failures directly to S3 because it sometimes causes you like 503 kind of errors. And from the cost perspective, I have like laid out a simple like architecture here. Suppose you have a Presto and that your data is cross-region, like both in S3 US East 1 and then S3 US West 1. And then if you don't use something in the middle as a cache, and you probably just have the frequent access as the calculation I did in the previous slides. And also, by after having a cache in the middle, it's actually cache the hot data, and then there's less requests directly from your cloud storage. Instead, hot data is stored in the cache, and next time when you're accessing it, it only like interact between your compute engine and the cache instead of directly from the cloud storage. In this sense, you're reducing the requests, and because that charge you request, you're reducing the cost. And also because it charges you by the amount of data transfer from network, it also reduces your egress cost or data transfer cost. And then let's see how does cache benefit the performance as well. We understand in a hypothetical view of the latency, you see the composition of latency include a time spent in really doing the computation and a time spent in I/O. So the cache can really reduce the amount of time spent in I/O, which means the total job runtime is greatly reduced. And I want to introduce Alluxio as a caching framework. I wonder if how many people have heard of Alluxio before, but we are most likely more famous in the non-real-time kind of workloads. But as you know, Presto is also doing near real-time. So I think the real-time and non-real-time, the boundary is now more blurred. So we have two types of different cache framework. The first one is we call Alluxio Edge Cache, or local cache in Presto. So it runs as a library in applications. So it's supported in Presto in Trino, and also you can use it in HDFS data node too. And it can leverage the local disk NVMe or memory on that single machine. So when you have you have an understanding of how much cache space you want to use. You have an understanding of your size of your hard data, if it can fit the single machine, and this one could be a good fit. And also, it also requires the scheduler to be aware of the, take advantage of data affinity. Bin will talk about detailed design later in his part. We also have a Alluxio distributed cache, which serves as a standalone cache service. So think about it as a scale-out type of distributed cache that you can use between the different compute engines. For example, you can share the data from the cache with Spark, with Presto, Trino, or further with your machine learning workloads as well. So these fit well when you have a lot of data to share. The cache space can exceed the amount of the disk space you have in your compute nodes. And as you can see, I'm from the open source side of community. I'm a developer advocate. I can tell you that not only this is a conceptual thing, and we have in production deployment in a lot of top internet companies, including Uber, that Bin will talk about later in his part. And we also have a very vibrant open source community. You can check out our Slack. We got companies deploying our thousands of nodes of Alluxio, which means we are production ready and we are being utilized in these top internet companies. And now I'm just going to hand it over to Bin to talk about some of the case study part.
Thank you, Hope. So let's dive into a little bit more into a case study, how particularly a user, if you're a maintainer or admin of a Presto or Trino or this type of data-intensive analytics cluster, how you can leverage the caching capability to reduce your cost, but also improve your performance. So a little bit more dive into the technical part. Okay, let's go through the easy part. Hopefully, this is something presented to you. You can, oh yeah, this is sounds straightforward. First of all, we have this multi-level different caching as mentioned by Hope. We view this edge cache is L1. It's embedded into the process, JVM process of a Presto or Trino, and Uber has a case study showing they also put this into data nodes as another caching library. It's very easy to use, open source, and also you can just leverage your local disk storage or SSD storage as this is a transparent caching layer in your process, Java process. Okay, so in addition to that, we can also lay out this Alluxio distributed cache as another service. And this will independently scale up and scale down, depends on how much data you want to store in this caching layer. So what we see, okay, so how do you choose between this, or how do you choose in the combination? Typically, if you have relatively small number of hot data, like total amount of data is controllable, and also you don't experience a lot of or if you want to get a very fast speed, the performance is what you care, then definitely the edge cache is, as a library, provides you the best performance. No RPC is required, extra RPCs. However, if you're looking for something shared, a data shared across different frameworks, across Spark, Presto, Hive, different type of engines, then you definitely need a separate service on that. So that is the Alluxio distributed cache. And also, from time to time, we heard from our customers that users that they have a peak time and a normal time. So they want to also scale up and down their capacity in terms of the caching, in terms of the size of the data. So that's definitely another thing good to have this distributed cache. Okay. So I want to dive a little bit more into this edge cache in the Presto, which is an open source project collaboration between Alluxio team and Meta in the beginning, and then we also collaborated with Uber later on. So essentially what we do is put this edge cache into Presto worker. If you're familiar with Presto, a Presto fleet has a coordinator and a worker. Coordinator is checking, making the scheduling, making the plan, query plan, and then distribute the work to the Presto workers. So we put this into a JVM, the Presto worker. So this Presto worker is engaging with Alluxio through a HDFS API compatible. That's more or less a standardized file system API in Presto world. And once you go through this Presto HDFS API for the data, if it's sitting in a local Alluxio cache, you just read it from Alluxio, local edge cache. Otherwise, it goes to the original code path by fetching the data from HDFS or S3, you can name it. And this is basically transparent to the applications. All you need to do is to allocate the disk space, set the quota, and makes a little, I think that's it, actually. In this way, we can support like a reading Iceberg, Hoodie, Delta, Lakes, or Hive tables. And besides, it's orthogonal or independent from the file formats. And it's very optimized for local NVMe storage. You can check the Presto blog. We have been working with Facebook on this for a good 3 years, 3 or 4 years running in production workload in Facebook. So everything's good. Okay. So yeah, a little bit more supports the fine tuning. You can do the LRU, cache replacement policy, or FIFO, or random-based eviction policy. And it's also, you can customize a different admission policy. For example, you can say, hey, what do you want to admit to this cache or not? And we also have the TTL, which means you have this data sitting in this cache. After a certain amount of time, you want this data to be evicted from this cache, and then you can set a TTL to this. In the end, we set the data quota. All these are in production in Facebook and Uber, and it's, I think they are pretty happy with that. Okay, so that's looks like it's easy, right? But it's never easy. So it's actually when you're onboarding to a real production workload, you see a lot of issues. Now I'm going more into like what is the challenges we see. Like for example, I take a case study because this is actually documented in one of the engineering blog on Uber, how we are working together on this to onboard Alluxio edge cache into Uber Presto fleet. So just a little bit more context. It's actually already the time we worked together with Facebook, has been running there for a year or two. It's pretty stable. A lot of things are pretty settled down. I thought it's going to be a project for a month or two. It turned out much longer. So let's see what are the challenges we see there when we're onboarding this. So first of all, it's quite different. The data in Uber is constantly changing. Uber is a real-time, a lot of insights are built on the real-time data. So they have a lot of hoodie tables, and there's a lot of partition change in the real time. And also, they have this very different setup from the previous work when we are working with Facebook and how the Presto cluster is set up. In the end, I think the most difference is Facebook has a lot of resource to put into the cache allocation. So the per worker cache size is much bigger than Uber. And also, the Uber has also relatively good amount of data, total data to cache. So that's all the challenges we see. Like after a few months, if we look back, oh, this is a difference, and how we can solve this one by one. It's all about like productionization problems. It's less to do with how we implement the technology. It's really based on the workloads, how you tune the system to make it work better. I hope you enjoy the story here. By the way, everything is this is published already in the Uber engineering blog. If you're interested, just search the blog. The first challenge is really the partition updates. It's a hoodie table, so they constantly change these partitions, and once the data is bringing up into the cache space, sometimes it gets stale, and sometimes only a part of the stale data in the cache and the later part are updated in their HDFS. So in this case, what you see is the query will fail because they read inconsistent data. And this is basically reflecting what needs to be changed in this supporting these dynamic data lake formats. And also, yeah, so this is particularly like what we want to solve, the dynamic data. Well, the solution is relatively simple. It actually just includes the modification time of these files into this caching information. So once you fetch the data, the coordinator of Presto will fetch the data from HDFS. It also pass down the information for the modification time for each partition files. So we will also make a decision not only based on the file name, file path, but also the modification time to decide whether you have cache hit or not, and to decide when you are going to evict the data. So yeah, basically the new partition with the latest higher, a larger modification time will get cached and evict the older. The trade-off is this is engineering trade-off. Like we can do better, but we just like this works well, so we just let the outdated partition sitting there until the TTL kicks off. Second challenge is it's very interesting. It's basically on the Presto side, it's like I have for this to scan the table, I have many different splits. Okay, so to decide how I assign a split into a Presto worker, it's based on something called a soft affinity, which is a hashing-based methodology to decide this. Given this split is from a file. Okay, and the offset and the file name, I will decide which Presto worker to query, to run this query. Okay, so this is called a soft affinity. So the default way doing this is actually not working. It is pretty working well in the Presto fleet in Facebook because their cluster is very stable. They're very stable, pretty much like there's running there and all the nodes are there. Okay, but we found during the collaboration with Uber, we found they have very different setting. So their Presto worker nodes can go up and down. So the coordinator may face a different pool of Presto workers from time to time. So like on time 0, you have maybe, I'm just making this up, you have 100 nodes, and you, based on these 100 nodes, you make the hashing assignment for the jobs, and that creates the caching layout, okay? But later on, you get one node down and one node on, then, or a few nodes more into this ring, into this pool. You have very different hash mechanism, and that means a lot of the previous nodes data cached on these nodes will no longer be effective. Okay, so the approach to solve this is basically make this as more like a consistent hashing ring that you get the neighbors to cover you. Once one node is down, you get the next node on this ring. So this is basically the original motivation for people to come up with this consistent hashing. When you are having a dynamic nature of a set of nodes, how do you make sure the churn of data is less? So exactly, if you check out the paper in the early 2000s, that's exactly the reason people come up with this idea of consistent hashing. Okay. The next challenge is very also interesting. We found, like in Facebook's case, the cache space is large enough, so we don't need to tune the cache a lot. But in this case, they actually have to work on the tuning to make sure only the most important data, or to make sure that I only admit the most important data. Otherwise, there's a called cache thrashing, and the new data is always pushing out all the existing data, so no effective data will be cached. Okay. So essentially, we provide this cache selection algorithm. It's basically a allow list. Only in this allow list, you're able to make them into the cache space. But anyway, so you can see during this onboarding process, collaboration process with Uber, there is a lot of engineering or production issues, like we need production ready issues we need to solve to make it fully work. Okay, so the test results, I want to just have a disclaimer here. So this is our in-house test running a TPCDS. We're not sharing any data from Uber in this stack. This is our in-house test, running a TPCDS in the cloud and show you how much performance we get, how much cost saving we're getting. Okay, so here this is the cloud cost saving, as mentioned by Hope. There is a API request cost associated with your data request. Okay, by running the TPCDS, once the data is there in the caching space, definitely we see like most of the data, this is trivial, like most of the data is already cached in the TPCDS. For the TPCDS, is already cached in the space. So you spend very little compared to the original API cost you have to make. There's very little, like less than 1%. You need to still query the S3 or GCS in this case. And also we see a large number of data, not only the APIs, but in terms of bytes, we're also saving like more than like almost 100% of data. I still want to just emphasize there's no black magic here. So in your first read, or code read we call, you still need to bring the data from cloud storage to the caching space, but depends on your TTL and how static your data is. You don't have to change that, like the follow-up queries will just hit that part. And this is also the TPCDS, our in-house TPCDS test in the cloud, showing how the edge cache can help the TPCDS in terms of performance, and shows we compared the Presto reading from S3 directly versus reading from Alluxio cached with the edge cache. See 20% to maybe 40%. That's like it's varying there, depends on query nature. But in general, we see very consistent performance, at least 15 to 30% for queries like this. We also have the latest change into Trino. If you check with the Trino community, Trino is using Alluxio as the default local cache for Trino worker. It's a very similar story here. So inspired by the similar work. So yeah, they also see very consistent work here. Well, one final thing is a very technical thing. Sorry, I just quickly go through this. In case you are interested in, like, hey, I'm running a Presto, there are different caching options there, and here are when you can use it, how it's going to help you. It's basically you have the metadata cache, you have listing cache, you have FRC cache, and the edge cache for input. And 4 and 5 are Alluxio edge cache, and distributed cache. These can help you to optimize for input and output. Okay, so that concludes our talk today. We are willing to take some questions in case you have. Oh, thank you. Oh, QR, yeah, please feel free to scan the QR code. This is our, I think this is a.
Thanks for the talk. So first question is, what's the basic unit for the cache? Is it like a full file, or is like some blocks in the file can be cached?
It's based on we call this basically, this is the file, and we have the logical chunks, or we call them pages, which is 1 megabyte in size. Basically, it's aligned on megabytes boundary. But it's also very good question, because we do see it, because they tend to be accessing footers and headers a lot, especially for this coordinate data. So that means, yes, because they're frequently accessed, they will be cached more.
I see. Yeah. So I think another one is, I think in one of the slide, the K is like a HDFS file path. and with the modification time. So how the query get the modification time? Like how does the query know this is the latest modification time, so that it can tell the cache to find
This
the
is
most
implementation
latest
details. Yeah, we are able to incorporate the timestamp for this modification time into this caching scheme as part of the key. Yeah.
I see. So I think another one is
Can you be louder a little bit?
Oh, sorry. Okay. So is the cache more like built more specific for certain system and the file format, or is like more transparent?
It's transparent. So it doesn't matter as long as it's a file or object. It has a key or has a name that should work.
I see.
Yeah.
Okay.
May I have your maybe which company are you working for?
Oh, I'm working with StarTree, software from StarTree.
Okay. So actually, I sent out previously the APIs and also this work to Xiang. Yeah,
Okay,
and to try to establish something because he told me there might be something in StarTree you can leverage. So we can talk this offline.
Right.
Yeah.
Okay. Awesome. Thank you.
Sure.
So this caching layer, which is on top of the storage layer, this is specific to Presto, or this can be used across compute engines as well?
Yeah, good question. So the question is this specific for Presto or this is a generic, it can be used? Yeah, it can be generically used by other JVM applications. So we built it for starting from Presto because we want to have a user, right? Well, okay, so two things. One is the company or the team or the project started building this distributed cache first. And that distributed cache actually is originally a part of Spark or sister project of Spark. It's incubated from the same lab, Berkeley AMP lab. Okay, so that part, we make it a general purpose, not only working for Spark, but also working for other applications, Hive, because it's RPC based. As long as I provide the HDFS interface, you can integrate with us. Okay, so that is the distributed cache. For the edge cache, it started from Presto, yes. But now, I know, Uber has one other blog we didn't mention today, that HDFS has they integrated with this cache library with their HDFS data node to make sure, hey, even I'm moving my HDFS data node to a slower disk, but more capacity. That's the ongoing project. There is a project like this there. But then we can exploit the temporal and the spatial locality by having this caching library in their HDFS data node. So it's actually worked after this project. And now I think as I just mentioned, Trino also integrated with this cache.
Got it.
Yeah.
Thank you. One more question that I had is, so one thing that you touched upon is that if the data is real time, then the cache will not be that useful. What other use cases do you think where caching doesn't really work that well?
I'm not sure I follow the question. Can you repeat?
What are the other not working use cases?
Good question. I can tell you what it works like, at least from my experience engaging with our open source users. First, for the data-intensive workloads, the batching workloads, definitely it works well. Like SQL queries or some Spark jobs, typically they have some temporal locality, especially people are looking for certain hot tables. That's very true, universally common in different organizations. They have one or two or few tables that's always very hot. Okay, so that is working. And the other thing we see recently more commonly adopted is in the machine learning and AI frameworks or that kind of workloads that the data is needed across different basically epochs. They're training the same data, same set of data, many times for weeks or even months, same set of data. So that has actually pretty good data locality too. So we didn't cover that. So lately we have a lot of customers and users in this AI machine learning training framework, the use case. Another interesting thing is we are actually seeing people are using this as a write cache. especially for ETL type of workload. If you want to, especially there's in the pipeline, there's a certain temporary tables. You write a temporary table, if you always go to S3 or GCS for that, not only it's going to be a little slower, but also you pay the cost, right? So if you can just write this temporary data into a caching layer, and just to enable the next stage for a pipeline, then it will just save your time and also the cost and the money. So that's are the typical ways we see how users are using us.
And another typical use case that is related with the storage side is that you can use Alluxio to federate the storage so that use Alluxio to as a single source of truth of all the storage you have. That is agnostic to whatever like compute engines you use. We typically see this when companies are having a lot of merger and acquisition behaviors. They have like different data silos and they don't want to always copy or move these data silos. They can use Alluxio as that purpose, which is not only for SQL or for machine learning, but also can be considered just like a single access point of your storage. So you can consider like, other than these use cases might not be really a good fit of Alluxio as your.
Yeah, she was talking about in our enterprise offering, we have the ability to build a abstraction that like mapping different storage resource into a logical file system. Like, so you can just present a global view to applications, although it's underneath it's S3, it's combination of S3, HDFS, GCS, and many different things. Yeah.
So it's it helps build the hybrid cloud kind of a thing using that. Okay.
Yes.
Got it. Thank you.
Yeah. Thanks for spending time with us. We will be here around.
Thank you so much. We have our emails here if you want to reach out, and we'll be hanging around if you have further questions. And thanks for having us.